Hello, welcome all. In this video, we discuss two more individual members of carboxylic acid family. They are cinnamic acid as well as crotonic acid, which are unsaturated monocarboxylic acids. First of all, we discuss the structure of the two. This is cinnamic acid. You can see that if you name by IUPAC 3-carbon acid, so it is prop double bond at position 2. So prop 2 enoic acid, and at position 3 you have phenyl. So what is it? 3-phenyl prop 2 enoic acid. In common naming, we can mark this alpha and this is beta. So it is beta phenyl, and this is commonly called acrylic acid. So beta phenyl acrylic acid. See that both cinnamic acid as well as crotonic acid are alpha beta unsaturated monocarboxylic acid, because see, double bond is between alpha and beta carbons. Now, due to the presence of this double bond, and you see that carbon carries different groups, it can exhibit geometrical or cis-trans isomers. So the question is, which isomer is cinnamic acid and crotonic acid? You can guess. I am writing phenyl group by the symbol PH, H here and COH. This is which form? Trans. So trans isomer is what is cinnamic acid. That is, the two hydrogens are on opposite side of the double bond. So the complete name is trans 3-phenyl prop 2 enoic acid. This is more stable because of steric effect. See, there is no steric crowding. Big groups are on opposite sides. So this is more stable, and this is a naturally occurring isomer. That is a trans isomer, and that is what is cinnamic acid. Then what about cis isomer? You interchange these two, H here and PH here, then two hydrogen on the same side. You get the cis isomer, that is commonly called allocinnamic acid, adding the prefix allo. Similarly, crotonic acid. What is crotonic acid? This is an aromatic compound. Instead of this phenyl group, if you put CH3 here, that is crotonic acid. CH3. So what about the IUP's name? 1, 2, 3, 4. So it is but 2 enoic acid. That's it. Very simple. Here also there is cis-trans isomerism. So the more stable isomer will be trans here also. CH3 here. Okay. So this is the trans isomer. And crotonic acid is the trans form, right? Which is more stable again. And the cis isomer means if you change these two, you get the cis isomer of this compound, and that is known as isocrotonic acid. Okay. So cinnamic acid and crotonic acids are the trans isomer of this molecule. Now regarding the source, cinnamic acid is found in balsam and resins, that is the sap of tree, whereas crotonic acid is rich in carrot. We go to the detailed discussion of cinnamic acid, right? Like preparation, properties or chemical reactions, and also uses. And crotonic acid go in a similar fashion. Once you learn the chemistry of cinnamic acid, crotonic acid is just a duplication. First of all, preparation. See, cinnamic acid is prepared from benzaldehyde. That's the starting compound. Benzaldehyde can be converted into cinnamic acid. Let me write cinnamic acid, pH, CH double bond CH, COOH. Okay. Now, you have 4 name reactions here. Claisen condensation, Claisen-Smith, Perkin and Knoevenagel. Okay, so here we are getting familiar with 4 important name reactions. Now see that all these condensation reactions are closely related to one which you know very well, that is aldol condensation. Aldol condensation, which is condensation of aldehyde or ketone containing alpha hydrogen in presence of a base, right? And you have learned its mechanism in +2 level itself. The base abstract a proton of alpha carbon forming a carbanion, and the carbanion then attack the carbonyl carbon, isn't it? Here also the mechanism is very analogous with slight differences. Okay, that's why in all these reactions benzaldehyde is reacting with, see here it is ethyl acetate in Claisen, it is acetone in Claisen-Smith, this is acetic anhydride or acid anhydride in general in Perkin, and in Knoevenagel it is an active methylene compound, here it is ethyl malonate. So what is common in all these reactants? They are all containing alpha hydrogen, that's the common thing. And this is quite reactive because of the carbonyl group, you know, it is highly electron withdrawing and forming carbanion which is resonance stabilized. Okay, that's what happens in aldol condensation also. So that is one thing. Secondly, you can see a base in all cases. See, this is sodium ethoxide, NaOH, sodium acetate and piperidine, all are bases. So benzaldehyde react with a compound which contain active alpha hydrogen, acidic hydrogen in presence of a base forming cinnamic acid. We are not concerned with the mechanism in detail. Anyhow, we can understand the reaction in a better way. Let's see, starting with the first one, Claisen condensation. Actually, basically, Claisen condensation is a self-condensation of esters in presence of base. Means 2 esters can undergo aldol type condensation forming beta keto ester. But here it is one ester reacting with another aldehyde. It is aldehyde here. So this is to be called crossed Claisen condensation. Anyway, what happens, you know, this base will abstract a proton from here and it become carbanion. Okay, CH2 minus, right? Abstracting a proton by the base, and it is now attacking this carbonyl carbon here. This will be shifting. So first of all you get it as, this will become O minus, but later on it will abstract a proton back and become OH, isn't it? That's a very common kind of change takes place in all these kinds of attack of carbanion. CH2 COOH. And subsequently what happens, you know, see OH and one H from here will go forming double bond here. So it becomes alpha beta unsaturated ester. And this formation is because, you know, it is in conjugation, so there is resonance stabilization with this carbonyl group. So it becomes now CH double bond CH, COOH. And what is the final step? It's only hydrolysis. You have to make it acid, right? So it will be, you are adding water, it will break like this, you get the product cinnamic acid. Clear? When you go to Claisen-Schmidt condensation, the difference is instead of ester we are taking a ketone. This is acetone here, and you have a base. So let's see what is the carbanion now. The difference is that carbanion now is coming from acetone, so it will be CH2COCH3. Okay, one proton is abstracted from this carbon, that is alpha hydrogen, and now this attack here. So what do you get now? You will be getting, it is CH2COCH3, which will lose water as usual, and it becomes CH double bonds, okay, COCH3. Okay, now here to convert this into cinnamic acid, you cannot do simple hydrolysis because this is a ketone group. So you need a kind of oxidation. That's why you have a reagent in addition here, NaOCl, sodium hypochlorite. So this is a kind of reaction similar to iodoform reaction, or in general haloform reaction. So this is a mild oxidizing agent here. So what happens, when this is treated with NaOCl, what happens? First of all, this methyl group get chlorinated, it becomes CCl3. Okay, and finally this will be broken, cleaved with water molecule, and you get cinnamic acid. And see the byproduct, you are getting a byproduct that is CHCl3, that's chloroform, which is similar to iodoform, in iodoform reaction. Okay, now coming to Perkin reaction. What is the difference now? Now the compound containing alpha hydrogen, acidic alpha hydrogen, is acid anhydride. So very slight difference only here. Let's see what's the difference now. You are using, for example, here acetic anhydride. So CH3CO twice O. So one alpha hydrogen is abstracted, giving the carbanion which is like this, CH2COO, COCH3, isn't it? This one that will attack here. So only difference is now this part will change. That's all. The reaction is very similar. So it is now CH double bond, single bond, CH2 COO COCH3. It will lose then as usual water from here and become double bond CH, then COO COCH3. Now here you can simply hydrolyze the anhydride group easily. Okay, so the next is hydrolysis, of course. So it will be now this group will be hydrolyzed, OH here and H here. So the difference here is that the byproduct is acetic acid. If you compare Claisen reaction and Perkin, it is interesting. Very similar reaction. Here it is ester, here it is acid anhydride. Here you get byproduct that will be ethanol, isn't it? This will be broken and ethanol is obtained. Here the byproduct is what? Acetic acid, CH3COOS. That's the only difference. You get cinnamic acid as the main product. Finally, Novi-Nagel reaction. What's the difference here? See that in Perkin, sodium acetate is the base used. In Novi-Nagel, we generally use organic bases like pyridine, piperidine, etc. And in all these reactions, benzaldehyde only is used, whereas in Novi-Nagel, it is both aliphatic as well as aromatic aldehydes are used. Okay, so Novi-Nagel reaction can be used for the preparation of crotonic acid also, but not these reactions, because here you have to take aromatic aldehyde, that is benzaldehyde, to give you cinnamic acid only. Okay, so let us see about what happens in Novi-Nagel reaction. Yes. What is the reactant here? It's an active methylene compound. Similar to this one, you have an active acidic alpha hydrogen. This is ethyl malonate. You can also equally use malonic acid itself. That also will give the reaction. Anyway, what do you get? Alpha hydrogen is abstracted by the base and it becomes the carbanion, which will be like this now. Okay, attacking here. So what do you get first? It becomes CH, OH. Okay, and this will be C, COOET. I am writing these two separately. There are two COOET separately written. What next? Next is, sorry, there is one H here, isn't it? One H is also there. What happens? As usual, it will lose water. So it is now pH, CH double bond C, COOET, COOET. Okay. Now, what happens next is that this will be hydrolyzed like this. Okay, and now you have two carboxylic acid groups on the same carbon, and which is unstable. So what happens, you know, that it will this will lose carbon dioxide from here. Decarboxylation takes place, and finally it becomes what? It becomes pH, CH double bond CH, and this COOH. You get cinnamic acid. You will have byproducts. 2 molecules of ethanol, okay, 2 molecules of ethanol, and there is also CO2. Okay, so these are various reactions responsible for preparing cinnamic acid. Okay, now on to the preparation of crotonic acid. We can do it here itself because it's very comparable. I told you that these reactions will not work for preparing crotonic acid because all these reactions require benzaldehyde or aromatic aldehyde containing no alpha hydrogen. But in nominal reaction, we can also use acetaldehyde, for example, that is aliphatic aldehyde. And what happens? We can now explain here using malonic acid itself. That also will react. So if you take malonic acid, COOH, okay. In presence of the base, this will become carbanion, then attack here as usual. You get the similar reaction. So only thing is that instead of pH, it will be CH3. That's all. The rest of the thing goes the same way, same reaction. Okay. So this is now replaced by CH3. You get crotonic acid by Novi-Noble reaction using this malonic acid itself. So the ester group need not be hydrolyzed here. This steps will be a little shorter. Okay. Now, in addition to this method of preparing crotonic acid by Novi-Noble reaction, another method, simple method you can say is starting from this compound. See, what is this compound? Tell me, what is this compound? This is not crotonic acid but crotonaldehyde. This can be easily oxidized using very mild oxidizing agents like ammoniacal silver nitrate, you know, like Tollens reagent, very similar to Tollens reagent. So if you use ammoniacal silver nitrate, it's a mild oxidizing agent. This group can easily oxidize into which one? Acid group. So you get crotonic acid. So these are important preparatory methods for these acids. Now we go to properties, or mainly the reactions. Okay. See, we will discuss reactions of cinnamic acid in detail, and for crotonic acid you make a duplicate. You have to practice reactions. Okay. See, when we consider reactions, see that cinnamic acid is having this structure. It has got 3 functional parts, groups. there's a double bond, so it can show reactions characteristic of double bond, like addition reactions, etc. It can show reactions characteristic of COH group and also reactions characteristic of aromatic ring. So reactions due to double bond, let us discuss first. Let us write the compound CH double bond CH, COH, cinnamic acid is treated with various reagents. Look, first of all, catalytic reduction, addition of hydrogen in presence of nickel. You know this reaction, what happens? This will add to the double bond, addition reaction, and this becomes saturated, isn't it? The product is CH2, single bond CH2, COH. You try to give IUP's name for all the products obtained here. That's your job. What about this one at least? Let us say 1, 2, 3 propanoic acid and 3 phenyl propanoic acid, isn't it? Okay, the rest of the thing you may do. Next is adding bromine. Bromine can be added. You can use bromine water, for example. What happens? Bromine get added. Again, addition reaction similar to this. So what is the product? You get 1,2-dibromo product, isn't it? This is broken. So it becomes CHBr, CHBr, COOH. Okay? What is the importance of this reaction, you know? Analytical importance. This can be used as a test for unsaturation. In the lab, when we do organic analysis, one test for unsaturation is by adding bromine water, because bromine is brown, yellowish brown color, and on adding this, the color will disappear when the reaction takes place. Coming to the next one, and this is treating with lithium aluminum hydride. Lithium aluminum hydride, that is a very strong, powerful organic reducing agent. What happens, you know? This will reduce both the double bond as well as the carboxylic acid group. What is the product on reducing carboxylic acid? We have learned this earlier on. You get primary alcohol. See that if the temperature is very low, like minus 10 degrees Celsius, lithium aluminum hydride will not affect this double bond. That's interesting. So keeping low temperature, you can keep this double bond intact only as it gets reduced. So the product is now CH double bond CH, CH2OH. Okay. But generally at normal temperature, lithium aluminum hydride will reduce both these, and then the product will be a saturated one, CH2, CH2, COOH. You understand the difference? Now coming to the next one, reaction with ozone. You know what is the reaction with ozone called? Ozonolysis. It will break the double bond, right? You might have learned this one in your plus 2 course. It will break it here, and simply it will be double bond CO, double bond C, C double bond O. You get 2 carbonyl compounds are obtained. Of course, this require, in addition to this, you will be treating with zinc, and isn't it? Zinc and H2O2 is also used here for this cleavage. Final product is obtained. So, what do you get here? This is broken into 2 pieces. One is this one. What is this? Benzaldehyde is one product. What is the next one? That's a very interesting product. CHO. This becomes CHO and COOH. What is the name of this compound? See, if 2 groups are COOH, what is it? Oxalic acid. If 2 groups are CHO, that is called glyoxal. Okay. In here, one CHO, one COOH. So interestingly, it is called glyoxylic acid. Glyoxylic acid. Okay. The next one is reaction with osmium tetroxide. Again, it's a kind of oxidizing agent it is, but it will not cleave the molecule. It is simply pi bond is broken and 2 OH will be added here. So you get it as CHOH, CHOH, COOH. Okay, you get vicinal diol. Okay, that's again oxidation. And actually this compound can be converted into this product on further oxidation using HiO4. Periodic acid can oxidize this product into benzaldehyde glycolic acid. That is there. And finally, a very interesting reaction is treating with light, exposure to light. See, cinnamic acid on exposure to light form dimers. Two types of dimers are obtained. To understand that, let me write simply cinnamic acid like this. There are two types of dimers formed by cinnamic acid. Due to the presence of double bond, two molecules can go for a kind of 2 plus 2 addition, a kind of cycloaddition. Okay, so the products are, if both molecules are coming in the same fashion, means the next molecule also comes in the same fashion, the product will be like this, pH. See, this pi bond is broken, you know. Let me write, for example, I am writing the next molecule just below. So these two are aligned in the same fashion. 2 pH on this side and 2 COH on that side. If this is added by breaking this pi bond, you get the product like this. Okay? You get like this. This is called truxinic acid. This dimer is called truxinic acid. Okay? IUPAC will be different here. If you number it 1, 2, 3, 4 is the cyclobutane basically. So it will be 3, 4 diphenyl cyclobutane 1, 2 dicarboxylic acid. If another possibility is that this molecule is reversed and undergo addition, it will be then what will be the difference? It will be now like this. The difference will be that pH will come over here and COH will be here. This is commonly called truxilic acid. Truxilic acid. Okay. So two types of dimers are obtained by exposure to light. Now next is reactions due to COOH group. That's very simple because we are already familiar with various reactions of carboxylic acid. We're discussing only a few. See, reaction with bicarbonate. Let me take, cinnamic acid as COH group. So with bicarbonate, what is it? Carboxylic acid will react and form sodium salt, giving out carbon dioxide. So you'll be getting the sodium salt of cinnamic acid. We can call it sodium cinnamate. The visible part of this reaction is that effervescence will be produced. So test for acidity it is. Next is treating with soda lime. If you heat with soda lime, you know this reaction. This is a reagent for decarboxylation. This CO2 will be lost, isn't it? So what is the product now? Product is interesting here. You are getting this compound that is called styrene. If you are using alcohol, treating with alcohol, carboxylic acid form esters in presence of, for example, acid. You get the ester of cinnamic acid, isn't it? It will be COOR. You get ester of cinnamic acid, or you get alkyl cinnamate, you can call it. And finally, treating with ammonia as well as PCl5. What are these reagents for preparing, acid derivatives? Here you are preparing ester, that's an acid derivative, and here it is to prepare amide. When treated with ammonia, it will first form ammonium salt, on heating it lose water, and finally it become amide, isn't it? CONH2. What about PCl5? For preparing acid chloride, OH will be replaced by Cl. These are all very familiar reactions to you. Already we discussed in detail on these reactions. Okay, now next is reactions due to the ring. See, you know that cinnamic acid has got a benzene ring, an aromatic ring, okay? So, it can undergo electrophilic substitution reactions. There are two questions. One is, what about this group, whether it is activating or deactivating? It's very simple. COH is electron withdrawing, vinyl group also is electron withdrawing, right? So, it is deactivating. That means cinnamic acid will react slower than benzene itself for various electrophilic aromatic substitution reactions like nitration, sulfonation, etc. If you carry out nitration, suppose concentrated nitric acid and sulfuric acid, nitrating mixture, where the groups comes, though it is deactivating, orientation is ortho-para-directing, because generally all alkyl groups in general are ortho-para-directing. So reaction is slower, and if a third takes place, you will be getting ortho plus para product, which will be major product. Which will be major product? It will be para product because because on steric ground this will be the major product. Okay, so that's about reactions of cinnamic acid. Then uses, cinnamic acid is used in preparing drugs, pharmaceuticals, dyes. In perfumery it is used. Also, it is a precursor in preparing the artificial sweetener, that is aspartame. Now on to crotonic acid. It's just an analogous discussion I am leaving to you. Preparation we already discussed. For the reactions, what's the difference? See, in crotonic acid, only difference is that instead of phenyl group, it is methyl group. So it will show all the reactions due to the double bond, what all we discussed. It will show all the reactions due to the acid group, and there will be no reaction corresponding to the ring. That's the only difference. So that's left to you for practice. You do it. So with this, we wind up all the chemistry of carboxylic acid and its derivatives. Thank you.